Tomasz Szarek from University of Gdansk or something like that. He's going to talk about ergodic measures for Markov semigroups.
Thanks, Martin. I'm very grateful to the organizers for inviting me here. It's a great pleasure and a real honor to be here to take part in this program. I think that the title of my talk, switch on my microphone. So registered my acknowledgement. So thanks for the invitation to this program. I appreciate to be here. Okay, I think that the title of my talk could be a bit strange for you, despite the fact that I am not an expert in stochastic differential equations. I promise to provide some examples at the end of this talk from the theory of stochastic differential equations, so some possible applications of this general results. These results will be formulated for general Markov semigroups, will be presented. These applications to stochastic partial differential equations will be presented at the end of my talk. Okay, we start with the following assumption. X and rho in our setting will be a Polish space, so it's complete separable metric space. As usual, by calligraphical B, we'll denote the space of all Borel subsets of X. And B of X and respectively CB of X, this will be the Banach space of all bounded measurable functions which are defined on this space X, and they are equipped with the supremum norm. Okay, Lip, this will be the space of all bounded Lipschitz functions defined on this space X. Well, we'll consider the transition semigroup of Markov family. If you prefer to look at Markov process, so we may have a look at this process. So this process will take values in the space X, and it will be governed by this transition semigroup. So this is a transition semigroup. This is a semigroup which is defined on the space of all bounded Borel measurable functions and transforms this family into itself. But we will have to assume additional assumption on this transition semigroup. So in our case, this semigroup must be Föller. This means that the space of all bounded continuous functions is invariant for this semigroup. So PT of all continuous bounded functions is contained in the space of all continuous bounded functions. So every continuous bounded function is transformed on a continuous bounded function. Okay, what we have to assume, what will be assumed during this talk, that this Markov family is stochastically continuous. Stochastic continuity means that if we take an arbitrary function, bounded continuous function psi, and any point x, and if we take this limit, so if we will converge with t to 0, we'll get psi of x, and it is satisfied for all bounded continuous functions. And the main hero of this lecture is so-called E property. So we assume that this semigroup satisfies the E property. I will give some comments on this condition later on. But first, the definition. We say that this transition semigroup, we have some transition semigroup, and this semigroup has the E property at some point x if the family of functions, so we take the family of functions, the iterates, in fact, pt of psi, they all will be, the whole family will be equicontinuous at x. And this condition will be satisfied for any bounded and Lipschitz function psi. These results, the results I would like to present here, originated in the theory of fractals, semi-fractals, iterated function systems. That's my field of interest. And it is a slight generalization of so-called non-expansive Markov semigroups, non-expansive with respect to, for example, Wasserstein metric, or there's many possibilities to introduce some distance between different measures. If these measures are, if this operator, the semigroup of operators is non-expansive, so it will have to satisfy this condition. This condition, for example, if we take the semigroup which transforms all functions with the Lipschitz constant, for example, 1, and this transforms the space of all such functions into itself. So if we take an arbitrary Lipschitz function with the Lipschitz constant 1, and after transforming will be still the Lipschitz function with 1. So of course this family in natural way satisfies this condition. We assume that this E property is satisfied at some point, but usually we will be able to show that this condition is satisfied for all x. So then the semigroup will have the E property if this condition holds at any x. Sometimes the Markov process, which corresponds to transition semigroups, or the other way around, if we have Markov process and corresponding semigroup satisfies the E property, sometimes this Markov process will be called E process. So if a process satisfies the E property, the semigroup satisfies the E property, so then this process will be called E process. And this condition is satisfied at any x, so then this E property holds. Okay, well-known condition introduced by Martin Heirer and Jonathan Mattingly in the Annals of Math paper, when they introduced so-called asymptotically Strong-Feller processes. So asymptotic Strong-Feller property, maybe I will give some comments on this later, but this property implies the E property. So any Markov process which satisfies the asymptotic Strong-Feller property possesses the E property. So here we see that it's possible to apply this general theory I would like to present here to stochastic partial differential equations, because nice results obtained by Martin and Jonathan for stochastic differential equations which have asymptotic Strong-Feller property says it. Okay. Having this Markov semigroup, we may define the dual semigroup. This is the semigroup defined on the space of all Borel measures, or all Borel probability measures. It is extended in a unique way to the space of the whole, even Radon measures or signed measures. This semigroup is defined by the following formula. If we take an arbitrary Borel measure mu, so on an arbitrary Borel set B, it is just the integral over x from of the function pt, the indicator of the set B. This integral is taken with respect to mu. So then we will get the semigroup. Obviously, this is also a semigroup defined on the space of all Borel probability measures. Okay, and an invariant measure we'll be talking about invariant measures for Markov processes. This invariant measure is just a fixed point for the semigroup, or this dual semigroup. So Pt star mu star equals mu star, and this condition must be satisfied for all t. So then we say that this measure is invariant. Well, the crucial role in our consideration, our talk, will be played by the set calligraphical t. I will introduce maybe a bit later about some definition. Okay, or some notation. If we have a t, capital T, which is positive, an arbitrary Borel probability measure mu, so then we may take Qt of mu as Cesaro mean of this iterate, so of this semigroup Pt star. There's the only place when we need stochastical continuity, in fact, to be able to define this Cesaro mean. If it's stochastic stable, so we know what is it, and this definition is correct. But it's the only place we use it. Okay. In particular, the particular case when these measures are just Dirac delta at x, so we will write Qtx. Fine. As I said, the crucial role is played by this set calligraphical T. The set calligraphical T, this is the set of all points x such that if we consider Cesaro means starting at this point x, this family is tight. We see, and we will see immediately, that's obvious, that the problem of the existence of an invariant measure is equivalent to the question if this set is non-empty. If this set is non-empty, so this family, in other words, there exists some point x such that the Cesaro means are tight. If they are tight, because this is must exist some subsequence which is convergent. The limit of the subsequence measure, which is the limit of the subsequence, is invariant. So it's almost obvious because we assume that this semigroup is a Feller semigroup. Without assumption that this semigroup is Feller, this condition does not hold. Okay. So we'll be asking about the non-emptiness of the set T. But what is more interesting here, that the problem, in some sense, the opposite problem is also solved affirmatively. So if we know that there exists an invariant measure for this semigroup, then the support of this measure must be contained in this set calligraphical T. The proof we know is not immediate. So, and the proof, but the proof is valid only, the theorem is valid only in the case when we assume that this semigroup satisfies the E property. For the semigroup, which is only Feller semigroup, this theorem does not hold. So we may provide an example of Markov semigroup such that we'll have an invariant measure, even unique invariant measure, but the support of this invariant measure is not contained in the space of in this set calligraphical T. So in other words, we will be able, despite the fact that this invariant measure exists, we will be able to find a point from this invariant measure such that if we start at this point, the iterates will diverge to infinity. Having only, or assuming only, Feller property. without the E property. E property gives, in some sense, stability, so it's impossible. But we don't know an easy proof of this theorem. It's long. I'm not going to enter into details now. Okay, we start with the following classical theorem, which is probably well known, but when we tried to find this in literature, we had some problems. So we provided a proof, the proof of this theorem. This is a nice and obvious generalization of so-called Krylov-Bogolubov theorem. We know that if we have a process, or maybe an operator, or the semigroup of operators, which lives on some compact space, so then there exists an invariant measure. So might be proved this, okay, this invariant measure exists because this family, if we take these iterates of these operators, this family is tight. So repeating this argumentation I told you a few minutes earlier, we may get that this accumulating point of this Cesaro means is an invariant measure. So this theorem, in the case when the phase space is compact, it's trivial. This is the Krylov-Bogolubov theorem. But what when this space is Polish space, but we know that this condition holds. This condition, what says this condition? This condition says that if we may find a compact set such that there exists some point x, and this condition, the upper limit of this Cesaro mean on this compact set starting at this point is positive. Okay, geometrically looking, what we have here? We have here that there exists some point x, and there exists some compact set. And this condition says that on the average, with positive probability, we will be visit this compact set. So if we start with some trajectory, this trajectory will be, on the average, visit with positive probability this compact set. Okay, it could escape from this compact set. It may not live on this compact set. So we may not prove this in the same way as Krylov-Bogolubov proved the theorem. But the proof probably known, but I tried to find it and I failed. But the proof is very natural. So what we do here, we define a functional which is invariant. How we do this? We take this Cesaro means which are positive on this compact set. So we assume that we have this compact set and some point x. And we take a sequence Tn such that 1 over Tn from 0 to Tn P S star Dirac delta at x of k ds is positive. And having this, we may define a functional using the Banach limit or Banach limits. We take, what is a Banach limit? Maybe I recall you. Okay, this is a functional which is defined on the space of all sequences, bounded sequences, which is invariant with respect to shift. It means that if we take some sequence x1, x2, and x3, and so on, so we get x1, x2. No. The same as, okay, because this is functional. So we get, sorry, I wrote down the definition of shift, but it is the same as limit of x2, x3, and so on. This is bounded functional, positive functional, so it means that for positive sequences, the value of this functional is positive. it's non-negative, to tell the truth. And it's bounded, the norm of this functional is 1. And what we do here, having this, we may define this functional, using this definition, we may define, maybe I will write it down here, we may define the following functional phi defined on the space of all bounded continuous functions into R. And this functional is defined the following way. Phi of f is equal to the Banach limit L of the integral from over x f d q t I maybe x, okay. And this is for all q t n for all n. So having some function f, we at the beginning take these integrals, so we get for all n, we get some value, and of course this sequence is bounded because it's less than the norm of this function f. And having this, we may define this functional. The problem is, sorry?
Put also add to the theorem that the very measured charges in the set k. We would stuff k greater than 0.
Yeah.
It could be added, yeah?
No.
No, it's not true.
Not necessarily. So it will follow from this proof. It must be.
Not necessarily true.
No. Okay, but that's not invariant measure. We start with this.
But at least there is one which charges k. So you say it's not necessarily.
It's not necessary as assumption because it will follow from this. That's true. This measure will be positive on this compact. Invariant measure we get will be positive on this set k, but
that's what you were saying.
yeah. I didn't catch. Sorry. Okay, so that's true, but we don't need to assume this. Okay, so having this, but the problem is in the case when the phase space is X, so we have the Riesz representation theorem. We know that this functional is represented by a measure. So this functional is just equal to f with the integral of x with respect to mu star, some mu star. And we may prove that this mu star is invariant. But in the case when we have only this condition, we don't know if this functional is represented. So the Riesz theorem fails. However, we may prove that any functional which is invariant, positive functional, may be represented as a sum of two functionals. First one is the Riesz functional, so the functional which is represented by a measure, and another one which is purely singular functional. So purely singular means that the only functional, Riesz functional, which is less than or equal to this functional, of course this inequality is satisfied on all positive functional. The only functional, Riesz functional, which is less than or equal to this Riesz functional is zero functional. So, and in the case of general Polish spaces, we may obtain all possibilities. So we may obtain invariant functional, which is purely singular, which is purely Riesz functional, and both terms are positive also. And using this condition, we may get that this Riesz functional, so the part of this Riesz functional is positive. And if this part is positive, so then this measure which represents this Riesz part is non-trivial. If it is non-trivial, so we may try to take the, okay, so then from the uniqueness of this representation, it follows that if we take here PT, we'll get the same. So we'll get the same. Here we get the same. This will be the same functional. It will be represented again. And from the uniqueness, we get that this measure is unique. So the proof is easy and standard. But the only thing maybe interesting in this proof is this representation theory. Okay, but working in infinitely dimensional spaces, we see that this condition is very hard to be satisfied. So compact sets in infinitely dimensional spaces are very thin sets. So to enter in compact set is extremely difficult. So to assure that we have that we visit compact set is not easy. Why? Because we're not in infinitely dimensional spaces. Every ball, bounded closed ball, is non-compact. But what we have only, using, for example, some estimations for stochastic partial differential equations, what we know only that we may visit some neighborhood of compact set, yeah? Some neighborhood of points, small ball. That's what we can do. We may, with positive probability, enter in some small ball, not in a compact set as such. So this theorem is completely, in this formulation, is completely useless in the case of infinitely dimensional spaces. Fine, but we may generalize this result for Markov semigroups which satisfy the E property. Okay, so assume that we have a Feller semigroup and assume that there exists a point, say Z, from X, such that every open neighborhood will be visited with positive probability. So we will have something to erase this, maybe. Okay. We will know that there exists a point Z such that every open neighborhood on the average, because here we have Cesaro mean starting at the point X. So there exists point Z, and there exists, and for any positive delta, we will be able, on the average, visit open neighborhood of this point Z.
Does X, can X depend on delta?
Yeah. X depends on delta, may depend on delta. Okay, if this semigroup has the E property, so the E property must be satisfied. Without E property, this theorem is not true anymore. But if this semigroup has the E property, then this point Z, belongs to this set calligraphical T. This set is the set of all points such that starting from them, we will get the family of Cesaro mean means will be tight starting at this point. Then consequently, we commented this. This semigroup must admit an invariant measure. So then this invariant measure exists. Of course, if we assume without, as I said, without the E property, this theorem is not valid. We may construct examples such that this theorem does not hold.
Should there be an X then?
Yeah, that's a good question. This property must be satisfied, but not at X, but at Z. It's enough to assume that this property holds at Z. So this formulation, we didn't specify that this, we assume that this property, the property is satisfied in, no, it states here that this property is in Z. Let me say something about this proof, because this proof is, as you will look at it geometrically, it will be obvious. It's almost obvious. What we have? We have some point Z. And assume, contrary to our claim, that this point does not belong to the set T. What follows from the fact that this Cesaro means starting at this point Z are not tight? From this follows, it's not difficult, from this follows that there exists positive constant epsilon. Sequence of times T1, T2, and so on. Sequence of compact sets K1, K2, K3, and so on, such that the following two conditions hold. If we take PT n star at this Dirac delta at Z on this set Kn, this will be greater than epsilon. So n and n, this index is the same, Tn, Kn. But these sets are separated. So the distance between these sets is greater than epsilon. So if we take infimum over all rho x, y, where x belongs to K n and y belongs to Kn, this distance will be greater than epsilon as well. It is not difficult to prove that from the fact that this family is not tight, it follows this condition. And what we have, try to draw this. We have point, some point Z, and we have infinitely many islands, compact islands, K1, Km. They are separated, yeah, in some distance. It takes place in infinitely dimensional spaces, so it's possible. Okay. And what we know? We know that for any open neighborhood of this point Z, we may find some point X such that starting at this point, infinitely many times we will be with positive probability in this open neighborhood. So this probability being infinitely many times in this open neighborhood will be greater than, say, alpha. So the mass which will appear here in this neighborhood infinitely many times on the average will be greater than alpha.
What did you pick the x, the point x outside the ball in your picture?
Well, because I don't assume that this point, what I assume here, I assume that this point, this is an arbitrary point. No, but because this is for some point. Such point exists. I don't know. This point is inside. It could be inside, sure. But I don't know. Okay, so if we have that this measure is greater than alpha, so what we have here? We have here that infinitely many times this will be greater than alpha. Okay, but we know that if we start at this point Z, so we'll be infinitely many times on some, taking these iterates, we will be on some compact sets. But what is almost obvious, if we take PT I star of this average Q, T, x, this is Cesaro mean, this will be almost the same as qt of x. If we take t large enough, so the difference, and it will be done, it will be assured uniformly. So this difference, because it's Cesaro mean, okay? So that's taking the image will be almost the same. Just okay. So if we take t large enough, but we may do this because this is infinitely many times, we will be with positive with the probability alpha in this neighborhood, and we have this. But look at this. If we start from arbitrary point in some open neighborhood of this, so this point may not be on all epsilon half neighborhoods of this compact set, may not be greater than on this open neighborhood. Not all points starting in this neighborhood may be greater than alpha half, epsilon half. Why? Because if all of them would be greater than epsilon half, from the Markov property, it follows that on this neighborhood we will still have more than epsilon half times alpha measure. It may not happen infinitely many times, yeah? Because if it will happen, if it would had happened infinitely many times, we would get that this measure is infinite, yeah? Because these sets, or maybe not infinite, but large as we want, because these sets are separated. So this will be different sets, disjoint. So this measure would, okay, so we may find one compact set and one point, at least one point, such that the measure on some neighborhood of this is less than epsilon half. So we see that on the point, at the point z, if we start at the point z, so p, t, and z on this point will be greater than epsilon, but on some neighborhood, epsilon half neighborhood, the measure starting at the point x will be less than epsilon half. What we get? We define here an arbitrary function which is 1 on k1 and 0 outside this open neighborhood. We are free to do this, so it's no problem. We can do this using Lipschitz functions. We can do this in the case of infinity dimensional spaces. We can use it see infinity or infinitely many times in the differential function, and so on and so forth. Okay, so we are free of choosing the appropriate family here. And having this function, we have some function f1. If we define this function, what we do? We may find in this open neighborhood, smaller neighborhood. What is smaller neighborhood? Such neighborhood that starting at these points, in these points in neighborhood, all functions, all integrals with respect to this function f1, so in other words, pt f of x minus pt f of z is less than or equal to, it's small, yeah, it's very small. So this function, as iterating this, will behave almost the same, yeah? Moreover, if we take pt1, so what we have? We have that if we take pt delta x and pt1, or maybe here pt1 delta x and pt1 delta z, so we get that this is satisfied, that only finitely many compact sets are important. What means that they are important? So there are only, because these measures for fixed T1 are tight, yeah? So only finitely many of them would have measure greater than 1 minus epsilon. So the measure on the rest of this set will be as small as we want. So we will repeat this procedure, starting at some big N. We'll repeat this procedure and find again another compact set such that some point in this neighborhood will satisfy the same condition. So we'll be able to find some close point which is close to this point Z, such that the measure starting at Z will be greater than epsilon, but the measure started at this point will be smaller than epsilon half. So we may again define here this another function and so on and so forth. In this way, we define series of functions because they are different supports. This series is a bounded function, Lipschitz, continuous, whatever we want, because these are defined on separated sets. And having this condition, we may prove that for this, if we take, for example, PTI of F, the crucial role in this series will be played by PTI-Fi. But for PTI-Fi, the difference between Z and Xi, which we found, will be greater than epsilon half. Moreover, the series Xn will tend to 0. If it will tend to 0, we will have contradiction to E property. E property at the point Z and E property with respect to this function which is given by the sequence. So it is a very simple geometrical consideration. Okay. What we got here? We got here that in this case there exists an invariant measure. But the next step, this is the question about the uniqueness. If we assume, same assumption in the previous theorem, so we assume that this point exists, so, but the difference is that X is, this condition is satisfied. In the previous theorem, it was satisfied for some X, so must exist X. But here, if we assume that it is satisfied for all X, then this measure will be unique. Moreover, we will be able to get something what is called star. I forgot how it's called. But we know here that is the Cesaro mean will converge to this invariant measure, but this will be satisfied only for nu which are supported in this set calligraphical T. If we start from outside this set, it could diverge to infinity. So this convergence is not satisfied anymore. Okay, so uniqueness, the difference is in an assumption on X. So in the previous theorem, we assumed that this concentrating condition was satisfied for some X. Here we assume that it is satisfied for all X. This gives uniqueness of an invariant measure. Okay, maybe I will skip this. Okay, and ergodicity. An invariant measure, we say that X generates a measure mu if mu is a weak limit of convex hull, but the closure is taken the weak topology. And the definition here, definition of an invariant measure, which is ergodic, it's natural here. It's known, well known. It's one of possible definitions. All of them are equivalent. Okay. So what we may prove? We may prove that if we have the E property, it was a bit surprising result for us, then the Cesaro mean converge. The Cesaro means converge. Okay, so if a measure is generated by some point, then the sequence has the same limit as the sequence starting at the point which generates this measure.
Isn't kind of this property like when you prove existence of a measure, that is the argument. That you start with some point, you take Cesaro means, you prove that tight, and then you prove.
Okay, but I started with particular point Z, and I proved that not that this point is tight. If it's tight, the Cesaro means are tight. It doesn't follow that Cesaro mean converge.
But that's somehow.
Some subsequence of this Cesaro means converge.
You said the whole sequence.
Yeah, that's true. A whole sequence will converge. Okay, but I have only 10 minutes, so I would like to, and then we assumed using the same technique, we assumed results which are well known from the paper by Martin and Jonathan, but for processes. So if we have a Feller semigroup and it admits the E property, then two different ergodic measures, that's the supports of two different ergodic measures do not intersect. Okay, so there are some results about topological irreducibility, but I think that you are waiting for possible applications to SPDEs, so I will omit this part of my talk. That's okay. What we proved also, we proved some criteria for the existence of finitely many ergodic measures. I don't know if it has any application to stochastic PDEs, but we may show this. Okay, but let us start with this application. We study the Markov process defined by the stochastic evolution equation of this form. Here R is the generator of a C0 semigroup. It acts on some real separable Hilbert space X. F, this is map which transforms the domain of F into X. R is bounded linear operator from another Hilbert space H to X. WT is a cylindrical Wiener process on H over some probability space. What we have to assume to be able to apply our results? We suppose that, of course, this stochastic differential equation has a unique Mite solution starting from some point X, and it defines, of course, a Markov family. And this process is stochastically continuous, which is easy to obtain. And the corresponding transition semigroup is given as expectation of psi of Zx of t. Yeah, that's for all bounded Borel measurable function. And we assume that this process is a Feller process, so this operator satisfies the Feller condition. We will assume that for this process there exists a Lyapunov function. What is Lyapunov function? This is a Borel measurable function such that it tends to infinity as x tends to infinity as positive function. And look at this deterministic part of our SPD. We assume that this deterministic equation defines a continuous dynamical, semi-dynamical system, But this system has a global attractor. This is a set which is invariant under the semi-dynamical system, and all trajectories will converge to this compact set uniformly on some bounded set. So we will start from 2 points. We'll be able, from all points in some ball, we will be able to find a time such that after this time, all trajectories will be in the open epsilon neighborhood of this compact set. And another assumption we should make is stochastical stability. It says that for every epsilon, every r and t, we are able to evaluate this probability. So this is the difference between stochastic solution and deterministic solution of this semi-dynamical system. With positive probability, the difference between them is less than epsilon. For stochastic differential equations with Wiener noise, it's easy to obtain. Okay, we may formulate the main result of this part of my talk. If this deterministic system has a global attractor and exists a Lyapunov function, this is technical assumption but very, very, very crucial. So it says that this trajectory won't diverge to infinity. So it will live in some bounded set. And this family is stochastically stable, and the main assumption here is that this transition semigroup has the E property. It's the most difficult part in prove that some transition semigroup has the E property. And this mixing condition or something like weak irreducibility is satisfied. Then this process admits a unique invariant measure, and ergodicity, this ergodic condition is satisfied. So starting from an arbitrary measure, Cesaro mean will weakly converge to mu star. If we assume that this attractor is a singleton, if this attractor is singleton, we see that this condition is satisfied, obviously satisfied, because but this is a kind of mixing on this attractor, this assumption. So in the case when K is singleton, so it's trivially satisfied. If this attractor is a singleton, then this semigroup is asymptotically stable. So even not Cesaro means, but iterates of this semigroup. So this semigroup, starting at arbitrary measure mu, will weakly converge to this unique invariant measure. If you would like to find an application to this theorem, look at the paper of Martin Heirer and Jonathan Matigli. The system, so this Navier-Stokes with degenerate noise satisfies all these conditions. I don't say that it could be proved, because as I said, the crucial point is to show the E property. What Martin and Jonathan made, they proved something what is called asymptotic Strongfellow property. Yeah, asymptotic Strongfellow property. It implies E property. Therefore, we may, using this theorem, obtain the same result. Thanks. Yeah.
Because you say that all properties. What about this singleton of attractor? Obviously, I don't know such result that for 2D Navier-Stokes, the attractor is a singleton.
But but uniqueness.
You mean there is no force?
Yeah. Well, that's this attractor is deterministic attractor for the deterministic part.
But I don't think they assume that they have no force.
Yeah.
Okay.
You can ask actually.
Makes no difference.
So
Makes no difference. But here he probably doesn't
But if you have no force, then the attractor is not singleton. If you have force, the attractor is not singleton.
Sure. But then this condition is satisfied. Why? Because 0 belongs to this formula 3. 0 will belong to this intersection of all possible points. So therefore, this condition is satisfied. So uniqueness of an invariant measure we obtain using this theorem. Of course, we don't obtain this asymptotic stability, but it follows from it. In the case when K is singleton, but we apply this result to passive tracer equation or passive tracer problem. This is joint paper with Tomasz Komorowski and Szymon Pesza. So in that case, this attractor was a singleton. So therefore, we got not only unique invariant measure, but convergence of velocity field or something like that. Okay, so that's all. Thank you for your attention.
I really don't understand. Is it possible to apply this theorem for 2D Navier-Stokes equation with deterministic additional force, or no?
Yeah, it's possible. Yeah. But to get what we want to obtain, if you want
to the unique, I mean uniqueness.
Invariant unique measure follows from this, but the problem is to prove in this case the problem is to prove
E property.
E property, yeah.
But it's possible to prove.
Yeah, because it follows. Martin, in fact, and Jonathan proved asymptotic Strongfeller property. But asymptotic Strongfeller property is a more general property, and E property will follow from. Hey, I'm right. Will follow from asymptotic Strongfeller property. In fact, we started thinking about this in different setting for iterated function systems. And when I saw Martin and Jonathan paper, I realized that what they obtained E property, in fact, but they call this asymptotic Strongfeller. In fact, I had problems to follow their proof, but I realized that E property follows from asymptotic Strongfeller. So this is application of this.
So
theory.
It can be any deterministic additional force, for example,
Sure.
for L2. Yes,
That's true.
It's correct.
Okay.
Any,
not
small.
It has to be smooth.
Smooth and not small. Or
Why
no,
smooth?
it doesn't. Well, because we need that.
How
Well, at
smooth
least
it has to
somehow
be?
smooth enough.
No, that's a good question, because I remember when
I don't
Jonathan
remember
was
how
talking,
much.
he was more or less assuming that everything is infinity.
Yeah.
So do you have force to be infinity?
Probably not. But the thing is, if the force is not in the range of the noise, then even though you have asymptotic Strongfeller, it's not clear you have irreducibility. So here you also had a sort of irreducibility assumption, and that one might become difficult
Yeah.
to check as well.
That's
Because if the force is in the range of the noise, then it gets ground. Okay. If it's not in the range of the noise, irreducibility might be very difficult.
condition 3.
Okay, so let's thank Tomasz again.
Thanks.